Okay, so this is lecture 21. We are going to be talking about linear programming. I think we're going to try to finish what we've been doing and then move on to the traveling salesman problem, which has an enormous wealth of applications. If anybody's looking for something good theoretically as well as applied to do, if you haven't chosen a chapter, the traveling salesman problems are very good. Right now, the main thing we're going to do is we're going to revisit the diet problem and realize how absurd the formulation was. All right, so diet revisited. So in the real world, what is absurd about the way we did the diet problem? If nobody thinks of anything, I will talk to dining today. I know the head of dining. Yes. Yes. Cost and taste. If there had been a couple of minutes before class today when things weren't working, we might have actually talked about binary connectives and whatnot. We care about things such as cost and taste. We're not trying to just minimize the cost. So here's the problem. Typically there's going to be a trade-off. When we looked at the knapsack problem had an absurdity in it, right? What was the absurdity in the knapsack problem last time? When we did the knapsack one, there's an absurdity. What was it? I'm sorry? Well, one is that we weren't considering the space of the knapsack. That's one. But when you looked at the three items, there was an absurdity. Yes. Yeah, there's one item you would never buy. Item 3 was just dominated in every category. You would never look at it. Oh, there's where the batteries are. I could have recorded the whole class today. Oh, what a shame. So it's easy in that situation not to take item 3. The trade-off is trivial. In the real world, however, there's going to be serious consequences, and you're trying to decide how much do I want to sacrifice for cost in order for taste. I know over the summer some of the students are able to eat in the faculty house, or they can eat at the Peresky. And for the students, usually it's not that difficult of a decision, faculty house or Peresky. Since this is being recorded, I won't say, of course, which one is chosen. Most of the time, there will be a trade-off. So how, you're consumers right now. Would you like to pay more for your meal plan and have better food?
How much more?
Exactly. That's exactly the question you want to ask. How much more? I'm talking about $1 a month. And we will have, culinary delights, 7-course meals. For $1 more, you clearly would do it. There is a trade-off. There is a point at which it's not worth it. And you need to find that point. So the difficulty in all this is we're comparing apples and oranges. For those of you who've taken probability with me or with somebody else, you might see or hear that all random variables are real valued. You never talk about how many head and tail. You would talk about maybe 1 and 0 or 1 and -1. This way you can combine different things. We need to somehow have a way to combine different constraints or a way of combining different more objective functions. So before we had ax had to be greater than or equal to b. We have to make the bare minimum. We had x was greater than or equal to 0. You are not allowed to regurgitate food. Okay? And then the objective was to minimize the cost, C transpose x. Let's try to maximize, I guess I can use a little t for taste, T transpose x. Okay, so I could try to maximize something like this for taste. Well, perhaps a better way of doing this is rather than using C and T, what if I then wanted to add a third thing? It's going to start to get confusing. So instead of using T and using C, let's use C1 and C2. So instead of now, well, I'm just trying to think of notation. And then you have to decide how much is 1 unit worth here versus 1 unit here. So we have two constraints. And so we want to somehow take these two things and combine them, it is extremely unlikely that the choice of x, which is feasible and minimizes this, also minimizes this. What's the easiest way we have to combine them? Weight them both by 1. You could do that. It's not going to matter. I would weight them by half if you want to combine them equally. It doesn't really matter. I could do 1/2 C1 transpose x plus 1/2 C2 transpose x. And if I do a weighting like this, the two constraints have the same importance to me. So I've basically chosen units or scales where each one of them is going to have the same value. If I had wanted both of them to be 1 rather than 1/2, would that have changed the answer? No, it would just change the magnitude of the quantity. All that really matters is the relative size of these two. So what can you say about the possible values of the first one? What does it range between? 0 to
0 upwards.
Upwards, how far upwards?
Ci greater than 0.
So I could take the weight here, I could take anything greater than or equal to 0. I think you can do better than just greater than or equal to 0. And we'll put weight 1, weight 2. We'll assume the weights W1 and W2 are greater than or equal to 0. And there's another assumption you can make about the weights. They add up to 1. W1 plus W2 equals 1. Is I'm trying to choose how much I want to weight the two. It really doesn't make sense to have one of them going all the way off to infinity, because I can always renormalize. The only way I can't renormalize is if the sum of the weights is 0. But if the sum of the weights is 0, I have no objective function. Or I have an objective function that is indifferent to all feasible solutions. And then any feasible solution is then an optimal solution. This is the I don't care about taste and I don't care about cost. This would be a really eccentric billionaire. Okay? So without loss of generality, you might as well assume that the weights add up to 1. There are times when you won't do it. The weights might actually come from natural quantities involved, and in that case, they may actually sum to something that's other than 1. Doesn't really matter, but this is typically a great way to go. Do we know how to solve a problem like this? Yeah, this is just now a regular standard problem. We can now apply everything we've learned. So it's really not that hard to do multi-objective programming. The difficulty is choosing what you want the weights to be. How many of you have done regression? Excellent. So when you're doing regression, you're trying to figure out the coefficients and the parameters. You want to try to have some kind of relationship. Let's say you're trying to buy a house. What kind of quantities might affect the price of the house? I'm sorry? Number of bedrooms.
Number of buyers.
Number of buyers. So it's not as stupid of an answer as it might sound, but we're going to have to work a little bit to justify the answer of number of buyers. If you have a market where you have a huge number of buyers, you can afford to have a high price. If you have a market where merchandise is not moving, you might want to have a low price and you beat the other items that are on the market. So it's actually a very good answer. Square feet. How big is the house? Number of rooms. Location. If you can walk to, say, Williams College, that's a desirable thing in Williamstown. So there's a lot of different factors that go in. And when you're trying to decide how much a house is worth, what they often do is they look at other houses that are similar and say what they've sold for, and they use that to get an estimate of what your house is worth. Well, how do you figure out what's similar? You're not going to find a house that's exactly the same location, same size, and everything. So if you're in a large metropolitan region, it's actually a lot easier to find things that are similar. I'm looking at houses that are within a 5-minute walk of a tea stop, that have square footage in this range, that have this number of bedrooms. And you'll actually have a large enough data set that you can do something like that. In Williamstown, this is much harder. And then you have to make decisions. How much do you weight various things? How much do you trade off more square footage for an extra bedroom? Would you rather have 4 medium bedrooms or 3 large bedrooms? See, a lot of it depends on your family situation. Okay. I will, on October 31st or the first class after that, I will bring in some candy so that you can try to come up with a way to optimize which candy you eat so that you can put this in practice. So you'll have a couple of days to think about this. My wife just sprung it on her kids yesterday in her class. Just gave them candy and had them try to figure out which ones to eat. She actually took your candy. She found where I had stashed it. But fortunately, I bought a bag of, I think, 240 candy bars, and her students didn't eat everything, so we'll bring some after. But you have to decide, and that's where the difficulty is, yes?
Just out of curiosity, where do people trick-or-treat?
I actually live in the central area for trick-or-treating. The area near the elementary school is prime real estate. People drive from all over Williamstown, park their cars in like the elementary school, and start trick-or-treating. So we have to have an enormous amount of Halloween candy, which is one of the reasons why the day after Halloween, my students always get candy, because there will be leftovers. Yeah, if anybody's looking to, okay, I'll talk about that after. All right. So what I want to do now is I want to talk about quadratic and beyond. And then after this, we'll move to Vandermonde matrices. So if I forget about Vandermonde matrices, yell at me again to do Vandermonde matrices. We've already talked about why quadratic constraints are difficult. So constraints are hard. Because all we have to do is x times 1 minus x equals 0. What does that do? If you could handle a constraint like that, what would that do?
Binary x.
Yeah, binary x. So it forces x to be in 0, 1. And if instead of binary, if you wanted trinary or ternary, x, 1 minus x, 2 minus x. Or you could just write numbers in base 2 and have a bunch of binary variables. So if we could handle a quadratic constraint, we could do integer programming. Integer programming is hard, so it's unlikely we can do this. It turns out you can handle quadratic objective functions. So if the objective function is quadratic in certain ways, you can handle it. I'm not going to go into that. It's just nice to know that it exists, that you are allowed a little bit of freedom with your objective function. And if you think about it, the objective function plays a very different role than the constraints. The constraints affect how you search. The objective function then chooses how you swap columns out. So it's not surprising that if the nonlinearity is in the quadratic aspect in the constraints, that's different than if it's in the objective function, that's different than if it's in the constraints. All right, so unfortunately, we can't handle constraints. But there are times when we can take quadratic terms and we can replace them linearly. What do you think it's going to cost us to replace quadratic or cubic or higher terms with something that falls into linear programming? More variables and more constraints, right? So this is the trade-off. Is it worth having more variables and more constraints? Well, it now sets it up to a situation where we can use the black box of the simplex method or some other things. So in a lot of cases, it's worthwhile. So what I want to do is I want to do the example from movies. So let's say we have ytm, which will be 1 if we start at time t, movie m, 0 otherwise. For simplicity, I'm assuming we are essentially images and we have one screen. Does images have more than one screen? Yeah. So this is basically, we're now modeling images. All right? You could, of course, add things for additional screens and whatnot, but let's just try to keep things simple. I want to look at the following term. P of x is going to be the product. M goes from 1 to m1 of ytm, and then the product m goes from m1 plus 1 to m1 plus m2, 1 minus ytm. So let's look at this. So m1 and m2 are going to be some numbers. Let's assume they're at least decent sized. M1 and m2 are at least 1. So this is clearly going to be at least a quadratic term. We can't handle this right now. Let's think about what's going on. What would it mean for p of x to be 1? So if p of x is 1, what would that mean? In some sense, this goes back to the joke we had from Feynman about the unworldliness of a quantity. You can write all of physics as u equals 0. Did we do that? And you just take everything, take the left-hand side, subtract the right-hand side, square it. So what would it mean?
I mean, the first product is all ones.
First product is all ones,
The YTM is all zeros.
and the YTMs are all zeros over here. So since this tells us it's 1 if we start a movie at time t, if we start movie m, and 0 otherwise, this would mean we have started movies 1 through m1 at time t, and we have chosen not to start movies m1 plus 1 to m1 plus m2. So this is a way of detecting which movies we've started at the same time. This could be useful to have an expression like this if you want to look at demand. If you have 2 action movies starting at the same time, you could ask, what's the demand for the new Star Wars movie? I'm assuming there's going to be a new superhero movie coming out in the near future. They seem to be coming out very frequently now. So we'll assume that there will be some superhero movie coming out in December at the same time as Rogue One. And if you said only that movie was showing at the theater, there's a certain demand it would capture. But if both movies are showing up, you might have somebody who's showing up who could go either way. And then some of them will decide to see Rogue One, some of them will decide to see the superhero movie. So the demand you would get is not going to be the sum of the demands of those 2 movies. The demand for those movies is going to be a function of what else is playing. And so you want to allow yourself detecting terms like this. So the question is, we want to somehow replace this with new variables and new constraints. There's a lot of nice properties binary variables have. So if y is in 0, 1, there's a really nice property about y. What can you tell me about y squared? It's also in 0, 1. So when you're looking at binary variables, the square of a binary variable is still a binary variable. And it turns out we can actually program this constraint without too much trouble. All right, so what I'm going to do is the following. So let's look at the sum. M goes from 1 to m1 of ytm plus the sum m goes from m1 plus 1 to m1 plus m2 of 1 minus ytm minus m1 plus m2 delta t greater than or equal to 0. And then the other one will be the sum m goes from 1 to m1 ytm plus the sum m goes from m1 plus 1 to m1 plus m2, 1 minus ytm minus delta t is less than or equal to m1 plus m2 minus 1. Okay. So I was divinely inspired. I wrote this down. Well, actually, I guess I was divinely inspired and I typed it up and then copied it. What do you think delta t is going to be? What values will delta t take on? I haven't told you. What do you think we want delta t to be? Binary. So we want delta t to be in 0, 1. So we'll put that in. And this should be detecting something. You know, D for delta, for D for detecting. What do I want to detect? Well, I probably want to detect if that product is 1 or 0. Now, what's really, really nice about something like this is instead of looking at this as a product, I could also look at it as maybe as a sum. Right? Every time this is 1, I would get 1. Every time this is 0, I would get 1 as well. So what should this sum be? If this product is 1, if I replace these products with sums, what would the sum be? M1, I'm sorry? M1 plus M2. Right? Because if p of x is 1, then these are all 1, these are all 1, and I'd be summing m1 plus m2 items. If p of x is not 1, if it's 0, then at least one of these terms is 0, and then the sum of everything would be at most m1 plus m2 minus 1. So in some sense, I have a very nice way of checking whether or not p of x is equal to 1 or not. All I have to do is look at this sum. If this sum is m1 plus m2, then we know it's 1. And if it's less than m1 plus m2, then we know at least one thing is 0. So in some sense, this goes back to what we did before, when we had this detector to see, was this quantity a greater than or equal to 0. Now we want our quantity to be greater than or equal to m1 plus m2. So it's really not that hard to just tweak this. So let's look at this expression now. Assume that p of x is 1. So if p of x equals 1, then we'll call this equation 1, and we'll call this 2. Then in 1, the left-hand side is m1 plus m2 minus dot dot dot. What's the only way this equation could be satisfied?
When delta t is 1.
So if delta t is 1, it's true. What if delta t is 0?
Less than or equal to 1.
I'm sorry?
If delta t is less than or equal to 1.
Yeah, so it looks like the first equation is fine no matter what we choose for delta t. So do we agree? If in 1, no info on delta t. In 2, this expression would be 1 minus delta t has to be less than or equal to m1 plus m2 minus 1. If delta t was 0, what would happen? It would be a contradiction. So the second one forces delta t to equal 1. So in the case when p of x is 1, these two equations force delta t to be 1. The first equation is indifferent. The second equation forces delta t to be 1. This is very similar to just what we did before with the a of x. Now we could do p of x equals 0. And then if you now look at 1, if p of x is 0, this sum here is at most m1 plus m2 minus 1. Now we subtract off m1 plus m2 delta t, and we want it to be greater than or equal to 0. What does that force delta t to be? So that forces delta t to equal 0, and now hopefully 2 should be indifferent. This one is going to be at most m1 plus m2 minus 1. No matter what we subtract off, we're not going to make it larger because delta t can't be negative. So this second one provides no information. So this is a way to detect whether or not that product is 1 or not 1. So products of binary integer variables can actually be handled linearly. And if you look at this, we only had to introduce one additional variable and 2 constraints. That's not that expensive. So I thought it was just worth seeing because a lot of times you will have conditions like this. You want to know, have all these conditions happen simultaneously. The nice thing about binary variables is each of these terms is either going to be 1 or 0. So if I want to look at the product being 1, that's the same as this associated sum being m1 plus m2. And we already know how to detect that. So this becomes just a nice way to review that. Okay. Any questions on this? So again, the point I want you to get from all of this is that there's a huge amount of things that we can code in the confines of binary integer programming. And this should give you a really good incentive to try to find good ways of solving binary integer programming problems. We have not discussed how to solve binary integer programming problems. This is where black boxes come in if you want to do something like this for the course. If you want to work on a chapter, this would be a great chapter to work on in terms of seeing theoretically what's out there. How would you actually go about trying to solve a binary integer programming problem in a reasonable amount of time? To my knowledge, we have good algorithms that get us close, but we cannot solve these problems completely. Fortunately, for a lot of things, being close is good enough. If you are a multi-billion-dollar company with revenues in the billions, if you can optimize things to within $20,000, for us $20,000 is a significant amount. For a company majoring in billions, no, not at all. Okay. So what I want to do is I want to do Vandermonde determinants, and then I'll talk a little bit about doing maybe an example of what we've all been doing today. How many of you have heard of Vandermonde determinants? Okay. So Vandermonde determinants, it's absolutely beautiful. And so this goes back to an extra credit question I asked. So when we were looking at basic feasible solutions, it all comes down to, are the columns of the matrix that correspond to the non-zero entries linearly independent? And if they are, we say that is a basic feasible solution, if the solution was feasible. And if not, it's not a basic feasible solution. And there are only finitely many possible basic feasible solutions. Right? One of the things is there's only finitely many candidates. Because if I have a matrix, if I have finitely many columns, and I want to look at, take a subset of them, if there are n columns, I have at most 2 to the n subsets. Or maybe one less than that if you want to actually choose a column. And then all you have to do is show that every choice has a finite number of possible solutions, and then you're done. And it turns out they either have 0 or 1 solution because they're independent. So there's only finitely many possible basic feasible. So the question I asked is, imagine I give you a matrix that has, I think, let's say m rows and infinitely many columns. Is it possible to construct an m by infinite matrix such that every set of m columns is linearly independent? So want any set of m columns to be linearly independent. How many say yes? How many say no? Okay. How many say it's okay? The answer is yes. How many people think it's only an existence proof? Either we can show that something exists, but it's going to be some kind of strange process, and we won't be able to write down explicitly what the answer is. That just, if it didn't hold, then some catastrophe would happen. Because we've got one person saying that it exists, but it's not constructive. How many people think it's constructive? Okay. A lot of it depends on what do you mean by constructive. It's nice to be a professor at times. Let's consider Euclid's proof of the infinitude of primes, which I'm probably going to be presenting in 4th grade later this year. Right? We talked about Euclid's proof of the infinitude of primes, right? And so, Euclid walks. We looked at P1, P2, Pn plus 1. Either this is prime or it's divisible by a prime not on our list. So this constructs infinitely many primes. Would you say it's constructive? If I wanted to, could I write down the 20 billionth element of my sequence? I wouldn't have a nice closed form expression for it. I would have to do a lot of work. But what I do is I can take the first, did I say 20 million or 20, what did I say, 20 million? 20 billion. I can take the first one less than 20 billion primes, multiply them all together, add 1, and find the smallest prime number that doesn't divide that. That's not already on my list. And that would be my next term. So if you're willing to accept that, it's constructive. It's not pleasantly constructive. So we could introduce that to the mathematical jargon. So you have to decide, what do you want for your solution? I don't particularly think Euclid's construction is wonderful. But it does give you a method that will give you an explicit list of primes. It just very quickly becomes intractable to use. And so I think we talked about how maybe we have on the order of about 40 terms in the sequence. So I'm first going to show you a way to do it that is I guess, somewhat constructive. And then we can argue exactly how constructive it is. And then I will show you a much better way that's really explicit. So the answer is yes. So what we're going to do is choose anything for our first column that's non-zero. So we start off with v1, which is not 0. v1 generates a line. All we have to do now is choose a vector that's not in that line. And that will give us the next one. So we now have, or maybe I should call it A1. So that gives us now A1 and A2. And A2 not on the line A1. Does everyone agree I can choose a direction not on the first line? I'm in m-dimensional space. This now gives me a plane. I now choose something that's not in that plane. So let's do something for explicitness. Let's choose a value for m. What value of m do we want? 3? Okay. So any three things have to be linearly independent. Well, choose A1, A2, A3, A3 not in the plane A1, A2. Now we need to choose an A4. How many planes do we have to avoid? 3. Choose A4, avoiding the 3 choose 2 planes. Is it possible to choose a vector that's not in those 3 choose 2 planes? Yeah. What's the volume of a plane? What's the volume of finitely many planes? And the volume of the whole space is infinite. The planes are basically zero-dimensional, they're basically zero-volume subspaces in R3. And so you can look at the intersection of them, say with the unit ball, they're going to cover a volume of 0. So I just choose something that's outside. So now I choose A4 that avoids those 3 choose 2 planes. Now I need to choose A5. So how do I choose A5? Choose.
You were doing this such that like if you pick so basically this is based on the property that no 2 columns are going to be direct linear combinations of each other. Like A1 is not going to be like 2A2, right?
Right, but it's more than that. I mean, A1 will not be 2A2.
So we can take like so it's possible that like A4 equals a linear combination of 1, 2, and 3.
Yes.
But as long as we don't pick all of those.
Correct.
4,
Correct.
All right.
Yes. And so what we need to do is we just need to make sure that A5 is not in any of the planes that already exist. How many planes exist at this point? 4 choose 2. So choose A5, avoiding 4 choose 2 planes. Dot, dot, dot. Okay? So this is a somewhat constructive way. Yes?
Are you eventually going to end up with infinitely many planes, though?
But at every stage, when I'm choosing my next vector, I only have to consider finitely many planes. So when I'm constructing my matrix at one column at a time, at each choice, there's only finitely many things to consider, and that allows me to choose the next one.
Okay.
So I'm never writing infinitely many things down.
Okay.
So I'm skirting the line, or the plane, depending on how you want to view it. Okay? Is everybody comfortable with this? Yes?
So I guess what you're doing there makes sense, but like just thinking about it intuitively,
Right.
if you have 3 independent columns
Right.
in 3-dimensional space,
Right.
I thought that would fill the basis.
Yes, and it does. But now you have a 4th one. But if you're bringing the 4th one in, you have to throw out one of the first 3.
Yeah.
And that's what's going on, is we're trading. Think of this as what we're doing in the simplex method. We're trading a
One
column.
set of 4 is obviously linearly dependent.
Correct. And so whenever I put in a 4,
As long as one isn't a scalar multiple of another,
Correct.
Totally fine.
Right. I should have bought the Barbie dolls because I was tossing them in probability. I can just use them as vectors and throwing them out. Right. So when I'm putting in A4, I've got to throw away either A1, A2, or A3. So I'm not looking at all 4 of them together. I'm only looking at 3 of them. Now here's an interesting. How many of you have ever heard about the quote about monkeys in Shakespeare? So the corollary is Shakespeare is a damn lucky monkey. Right? If you have infinitely many monkeys typing at infinitely many typewriters, eventually one of them will give you the complete works of William Shakespeare. So Shakespeare is just equivalent to a lucky monkey. An extremely lucky monkey. Yeah. Imagine the monkeys get tired of banging on a typewriter and they decide to start learning LaTeX and doing mathematics. Because we're not going to have them doing this on a typewriter. No shift keys. I mean, come on.
You can do it on a typewriter with it.
You'd have to have a special typewriter.
Sure.
What do you think the odds are if the monkeys are randomly choosing real numbers and say 0, 1 for their entries? What do you think the probability is that the monkeys choose a m by infinite matrix where all the vectors satisfy the constraints such that any m of them are linearly independent? If you had the monkeys just going like this, what do you think the odds are that the monkeys would do it? High or low? High. The likelihood that you land in one of these lower dimensional subspaces is really small. So in some sense, the answer to this problem is not only is it doable, but with probability 1, anything you write down will work. Okay? So almost anything you write down will work. Now, if you try to write down a specific thing, then you have to prove it works. Years ago, I was TAing a linear algebra class, and the professor phrased one of the exam questions incorrectly. He wrote, give a vector that's linearly independent with the others. Did not say prove, did not say show, it just said give. So all of us graders were stuck going through and proving that the actual choice worked. Because if you write down almost anything, it will work. You have to work hard to find something that doesn't work. Yes?
I have sort of a probability question.
Oh.
So you were just talking about how if you, like with probability, it's basically probability 0 if you choose a random vector.
Yes.
That will be dependent on anybody. So is it for this just saying, because valid construction just say choose like any number of random vectors, and then with probability 1 it would be correct?
So the question is if you can just say with probability 1 we'll be fine up to these points, but then we have to worry about what happens in the limit, and you have to make that rigorous. I think it can be done because at every stage the probability is 1. You have to just make sure it doesn't all of a sudden collapse. I think it can be done. What I want to do is I want to give you an explicit solution using Vandermonde matrices. So here is an example that will work. So imagine I give you the matrix. There's several different ways of writing down Vandermonde matrices. Which way do I want to do it? I'll do it this way. 1x, 1, x1 squared, x1 cubed, x1 to the n minus 1, 1, x2, x2 squared, x2 cubed, dot, 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 x2 to the n minus 1, dot, 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 1, xn, xn squared, xn cubed, dot, 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 xn to the n minus 1. So here's my matrix. And I'll say that the determinant, I'll call it v of x1 through xn. And this is the determinant. No, it's different than that.
Is that not relevant, though?
It's not relevant.
Okay.
So I claim that if you take the determinant is going to be a polynomial in x1 through xn. Well, that basically is just from the properties of a determinant. We have this massive expansion, right? And you have to worry about the signs. Are the signs positive or negative? Can somebody give me a value of x1 and x2 that will make the determinant 0? 1 and 1. Give me another value of x1 and x2 that make the determinant 0. Okay, so if x1 equals x2, the determinant is 0. In general, if xi equals xj, the determinant is 0. Everybody agree with that? So what I know is the following. V x1 through xn is equal to some constant times the product 1 less than equal to I less than j less than equal to n of xj minus xi. And I may have things backwards. I'll worry about that later. I forgot to prepare this. So the first claim is part of it is no problem. If xi equals xj, the Vandermonde determinant is 0. So that means it's got to be divisible by xi minus xj or xj minus xi. So clearly, this polynomial over here, this product, clearly divides the Vandermonde. What I'm claiming is that what's left over is a constant. There's no more x dependence. That's the harder part. But it's not too bad. So let's look at what happens. The way we get a term is we take one element from each column and one element from each row and multiply them together. So let's look at the degree in the x's for a term in the Vandermonde expansion. We get nothing from this one to the first power from here, to the second power from here, to the third power, all the way up to the nth power. Right? So each summand has degree 0 plus 1 plus n minus 1, which is n minus 1 times n over 2. So glad that we spent some time early in the semester proving what that equals. It's an extremely valuable sum. I will also be proving that in 4th grade later this year. Let's look at the power of x over here. What would be the degree on the right-hand side? I'm sorry? How many pairs do we? We have n choose 2 pairs. And n choose 2 is n minus 1. So they're written in the opposite order. Here it's n minus 1 times n. Here it's n times n minus 1. Big deal. They have the same degree. There's no room for any more x dependence in the Vandermonde expression. All that's left is this constant c. So now we just have to figure out what c equals. There's only one value of c that would kill us. What is the one bad value of c? 0. So all we really need to know is that c is not 0. If c is 0, then it means it doesn't matter what values you take for the x's. Any value you take, you're screwed. Can anybody come up with a nice way to prove that c is not 0? All you need to do is find one choice of the x's where the determinant is not 0. So technically, I should call it c of n.
So
yes.
It has to be finally the determinant like 1, 1, 1, 2.
Right. So unfortunately, c does depend on n. So you can't quite do that. Good try, though. All we need to do is choose some x1 through xn such that c does not equal 0. So need cn not equal 0. Any thoughts? Yes.
Are xi's positive?
If you want them to be.
Do they have to?
No.
Okay.
No. They can be anything you want here. So any thoughts on what you want for the x's? So when you look at it, we're going to have a huge number of terms, right? All I need to do is make sure that one term in the determinant expansion beats the crap out of all other terms. Which term do you think is going to be the biggest term when we look at the determinant expansion? Let's choose maybe a relative ordering of the x's. Which x do you think is the largest? Yeah, why not? We might as well make the last one the largest. So without loss of generality, xn is greater than or equal to xn minus 1 is greater than or equal to xn minus 2. We might as well assume that they're put in increasing order. If they're put in increasing order, which do you think is the largest term in the determinant expansion? I'm sorry? Well, that's going to be the largest term in the matrix, but this is going to occur in a lot of expansions. Which term in the determinant expansion will be largest in absolute value?
xn minus x1 in your product.
But I'm saying which term? This is about n factorial terms, right?
The last term.
That's the largest term in the matrix. When I expand by, I get a lot of terms when I expand this determinant. Yes?
Is the bottom right 2 by 2 determinant?
Nope. The main diagonal. Right? Every term has to have 1 from each row and 1 from each column. If I'm going to choose 1 from this row, which one do I want? This one. Because this has the largest number of times. Now let's look at this column. I can't choose this again. Let me choose the second largest. So the largest term is going to come from the main diagonal. Okay? So when we look at all the terms in the determinant expansion, the largest is x to the n minus 1, x to the n minus 1, n minus 2, dot, 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 x 2, and then 1. So how many terms are there? There's at most n factorial terms. It's not that bad. But what I want to do is I just want to make sure that this number is large enough. So I could take maybe x2 equals n factorial, x3 equals n factorial to the n factorial, x4 equals maybe n factorial to the x3, something absolutely ridiculous like this. If I take something so ridiculous like this, the main diagonal term is going to beat the crap out of everything else, even if they all align. And this is enough to prove that in this special case, the determinant is not 0. So this proves Cn does not equal 0. Another thing we could do is we could try to match coefficients. When we look at this, the coefficient of x to the n, xn n minus 1, xn minus 1, n to the n minus 2, dot, 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 x2, x1, that coefficient is 1 when we expand this out. So when we look over here, if we want the coefficient to be 1, it actually, I think, forces Cn to be 1. So I think with a little work, you actually prove Cn equals 1. If it's not 1, it's negative 1. I'm at most off by a minus sign. And now this solves our problem. We want to have a matrix where we have infinitely many rows, and all the rows are linearly independent if we choose only m of them. Well, what this is saying is the only way this determinant is going to be 0 is if 2 of the x's are equal. If all the x's are distinct, the determinant is non-zero. So here's one solution. 1, 1, 1, 1. 1, 2, 4, 8, dot, dot, dot. 1, 3, 9, 27, dot, dot, dot. 1, 4, 16, 64, dot, dot, dot. It's a really nice explicit answer. So this is why I love Vandermonde determinants. They give you an explicit way of attacking stuff like this. All right, so this is a good place to stop.